Somebody made a basket in physics. Woo! All right, moving on. I'm sorry, what? Did you say something that was relevant to me?
Oh, no.
Okay. All right. So we had looked at this one yesterday. Yes?
Yes.
In which we're comparing the titration of a strong base with a strong acid and a weak base with a strong acid. We definitely could tell that this is the strong base because it starts close to 14. This is a weak base because it starts way, well not way, but significantly less than the 13, 14 range. We also get this little curve here, and also the inflection is quite a bit smaller. Good to go on that, right? Now, I think we pointed out the inflection here for the strong, the difference between the two. The midpoint is here, which is at 7. The midpoint here for the weak base is less than 7. Awesome. Okay. Because now we find out what the pH is, and there we go. All right, moving on. If we've already looked at that one, then the only thing we have left to look at, I believe, is a polyprotic acid. Is that what you guys have? Now, as you guys know, with polyprotic acids, there's more than one hydrogen that can be removed. Here we're looking at well, anyone want to take a stab as to what the name of this is? Yeah, it's phosphorus acid, because phosphoric acid would be H3PO4, for a phosphate ion, okay? Anyway, this is a triprotic acid. So once again, initially we recognize that it's a weak acid because its initial pH is, higher than 1. And then, okay, we get our little maximum buffering region. Where is pKa equal to pH? Don't look back. Where is pKa equal to pH? At about what volume?
75-ish.
For the first hydrogen. About what? 25-ish, right, because the equivalence point is at 50 milliliters, so we're talking half equivalence, where there's equal amounts of acid and equal amounts of conjugate base. You guys remember that? Okay, so the first pKa would be here. The second pKa would be here. Okay? Good, all right. I just want to point this stuff out. A lot of times, these are very good multiple choice questions. You guys remember that you've seen multiple choice questions where they'll just give you one set of information and then ask you like 2 or 3 or 4 questions related to that information. This is an excellent type of one of those kinds of questions. All right, anyway, moving on. So obviously you're seeing we're getting 2 inflections here. As we continue to add base, what are we going to see, do you think? Because currently what we have here, we've removed one of the hydrogens here. Now we have this remaining. We're removing the second hydrogen. Now we have this remaining. We'll see a really small, almost just a little bump up in inflection because if you remember, I don't have it up there anymore. When we got to the really, really weak acids, it almost looks like a straight line all the way across. You guys remember seeing that? Okay, if you look back on your graph, you can probably see that too. Okay. Actually, no, that's 3 graphs ago. Okay. Was that the last of your graphs that you have there? Awesome. Okay. That should be the end of the packet as you currently have it.
Yes.
All right. Well, give me 14 seconds.
Or 32.
You've returned to brown. Okay, good. Never mind, that was nice. return to tan.
But I
How
have.
about you?
I think I saw something earlier too.
I know.
There's skill up from like 8 years ago. I'm pretty sure he's like coaching some team in like Argentina or some other South American country. And I think like we were trying to set up some sort of charity game between our team and his team. So that'd be pretty sweet. I think it's like Boca Juniors.
Ooh, this didn't do it the way I really wanted to do it. Darn it. My bad. Got 3 coming to you. I'm giving bottom page first. Bottom page first. Yeah, come on.
Like, blue shorts make sense there.
Where Carson left again.
That will not. Might not be written down. Give me his
We have an equation.
You guys memorize your equations? No way. Gosh, that's mean.
1K.
That's mean making people memorize equations.
Oh, wait.
I don't even make you guys memorize equations. You just have to memorize everything else. You have to know everything all the time. Right, Mackenzie?
Oh,
It's not very
trickster.
secretive when I can still see
He gave us
everything
the
out.
second page first, so it's like Mr. Layden, the big trickster.
I don't know. I just grabbed them as they came out of the
Said we
thing.
have to enter the defined each variable. Or not necessarily defined, but it's yes.
What is it?
This paper feels sicker than normal. You guys noticing that?
Yeah.
Confusing you.
That's the highlight.
See, I didn't even bother to memorize the last two.
Do you know what the worst part of it is?
Those are just shoot. I didn't
That's so much.
Hey, listen, let's put them on the back. I'm coming around with the stapler. Add them to the back. Add them to the back.
Over here.
I'm good to go.
Yeah, I know.
Just chemistry and
Oh, yeah.
Chemistry is 4.
I figured it's because we're actually playing.
Very good. This is
But there's this one that I mean, apparently it's in 6 days, right? And so in the primary key, it's like 1, 2, 3, 4, 5, 6. And what happens
I'm good.
is, let me write the rhythm down real quick.
Okay,
Oh, yeah.
I got back and for each year. Like you're back, I'm like, I wait for one day and you got.
Is anyone?
Mary.
All right. Now that you're all turned to that front page, I want to point something out. On the front page, on the little set of outline here that we're looking at, we've already done common ion effect. We've looked thoroughly through buffer systems, titration curves we just got done. Next is molar solubility. The two main topics there are, sorry about that, main topic is solubility product. And the concept we're going to look at there, molar solubility and Q versus KSP. That's what we're doing today. Like I said, the title of chapter 17 in the book and on here is Applications of Aqueous Chemical Equilibrium. This ties it all together. If you haven't figured this out already, this is tying everything together. And if you remember those last 2 bullet points we're going to cover tomorrow, that's pulling in that last piece of chapter 19 and the last piece of chapter 20 that we haven't covered yet. So this is it. It's a great way to review. All right, don't need that anymore. And you don't need. All right. This is pretty interesting stuff. Shoot, I don't have a copy. Here we go. Solubility product, or KSP. Oh, look, I messed up my little parentheses. I got in a hurry there. Oh, well. Anyway, the solubilities, if you remember, we've talked about solubility before, but the only thing we worked at or looked at there was the relative solubility of things, soluble or insoluble. Is it going to precipitate? Remember the solubility guidelines? Precipitate or not precipitate. That was all we were concerned with. Now we're going to look at the extent to which something is soluble with a numerical value. Okay, that's what these KSPs are going to be used for. If you may remember from either your freshman year and or regular chemistry, solubilities are often given as grams of solute per 100 grams of water, which is 100 milliliters of water. Okay, so if you look at the solubility of sodium chloride, it comes out, and I can't remember the exact number, it comes out to like 36 point something grams of sodium chloride per 100 grams of water. At which point, when it reaches that point, it's called a saturated solution. Okay, we talked about that before. All right, anyway, as I mentioned earlier, KSPs are derived from saturated solutions in which there's some undissolved solid present. I already actually showed a couple of those to you so you guys could kind of hang your hat on that a little bit. When working these problems, the solubility can be determined or will be determined as molar solubility, you know, the number of moles of stuff that can be dissolved per liter of solution. However, we can convert that to grams if necessary. I'll show you why we're able to make that leap. And then this is usually most applicable with low concentrations of salts. And I will say this, with ions that do not hydrolyze. Now, what I mean, what does hydrolyze mean? It behaves as a weak base. Something that undergoes hydrolysis acts as a weak base. Okay? The sulfide ion, as it turns out, since it's relatively highly charged, will behave as a weak base. So this is not as applicable to like sulfide or something like that. All right. We're going to start looking at KSP expressions. This shouldn't be too much of a shock to you since we've been doing K expressions for a while now. However, there's a little, well, something to consider. If we were going to look at the solubility of aluminum hydroxide, for reasons that you may or may not be familiar with, you may recall that this is going to be what we would consider to be an insoluble substance. Okay, dissolve this stuff in water, we're going to get some aluminum ion, and how many hydroxides? 3. There you go. 3 hydroxide ions. Okay. If we're going to write the equilibrium expression for this, what would it look like? Well, it's going to be the concentration of the aluminum ion over, or times, the concentration of the hydroxide ion cubed over no. Because that's a solid, and remember we don't include pure solids or pure liquids in the equilibrium expressions, okay? So please don't make that mistake. We're looking at solubility products, KSPs. This will not be involved. Okay, easy enough. Next, let's start actually using these things a little bit. Question number 8. And now here's the thing, this is all equilibrium kind of stuff, so I'm not expecting a huge leap of faith here. We want to find the KSP of silver chromate that forms from a saturated solution that has been analyzed for the silver ion. So what happens is we take this silver chromate, it's going to be relatively what we would call insoluble. Well, as it turns out, when we say insoluble, there's going to be, as we're going to find out, a really tiny amount that does dissolve. We can find out how much dissolves by picking an appropriate substance that can measure the amount of one of the components. Okay? In this case, we're going to analyze it for the silver ion, and it's been determined through this analysis that the concentration of the silver ion ended up being 1.3 times 10 to the negative 4th molar. So we're talking a little over 1/10,000th of a molar solution. That's the extent to which it dissolved. That's pretty small, wouldn't you agree? Okay, so anyway, how are we going to do that? Well, remember that silver chromate, when it dissolves, since it's a relatively insoluble salt, it's going to be a equilibrium scenario. So we're going to get this. Now, we can look at this as an ice table if we want. This doesn't apply because it's the solid. We don't care about that. Initially, there's 0 of these things. To change, this is going to, well, what is this amount going to do? Increase by 2x. You guys are getting good at this stuff. And this is going to increase by x. So at equilibrium, we're going to get 2x and we're going to get x. Would you guys agree? Okay. Something else to consider here is, we already know the concentration of the silver ion, and that is, it was provided in the question, it was 1.3 to the negative 4th. Okay, so if that's 1.3 times 10 to the negative 4th, yeah, that's just what it was. Okay, we've analyzed it as 1.4 times 10 to the negative 3rd, or 4th. What is the chromate ion going to be? It's going to be 1/2 of that through the stoichiometry. So I'll show you how we get that. So it's 1.3 times 10 to the negative 4th molar, sorry about that, silver ion times, and you look at the stoichiometry, it's 2 moles of silver for every 1 mole of the chromate. I'm just doing the stoichiometry here. For some people aren't as comfortable with doing that in their head. Many of you are, that's fine, probably faster. Some of you would prefer to actually see the actual stoichiometry. So there it is, and it turns out to be 6.5 times 10 to the negative 5th molar in chromate. So all we have to do to determine the KSP is take these 2 concentrations that we've just determined, and one was analyzed, one was calculated, plug those into the expression. So we get 1.3 times 10 to the negative 4th times 6.5 times 10 to the negative 5th. That quantity is, whoa. Am I doing the right? Oh, I didn't write the equal. My bad. I was looking for a shortcut there. Let's go ahead and write the KSP for this reaction. My bad. Which was the, what are we looking at? Silver. And that is squared times the chromate. And so now we can do it. So we're going to go the 1.3 times 10 to the negative 4th, quantity squared, times 6.5 times 10 to the negative 5th. And whatever that comes out to be. What'd you get?
8.45 something like that, but it's oh, sorry.
Yeah, I was gonna say, I didn't get that. Maybe I did.
I got 1.1 times 10 to the negative 12.
Same.
That's what I got.
Yeah.
You just forgot to square it, possibly?
Yep.
So 1.1 times 10 to the negative 12. And that's the KSP. Now, as far as an equilibrium constant is concerned, what would you guys consider this to be?
Very,
Really, really small, which we already had a pretty darn good idea that that was going to be the case because of this right here. Okay, so there's one thing. We can calculate a KSP from some experimental data. Here's another way that we can do this. In this case, we probably precipitated out the silver chloride with another sort of anion just to get this information. Let's tie in stuff that we've recently learned and apply that to the KSP scenario here. What if we have a solution of calcium hydroxide? Now, what do we know about calcium hydroxide? What type of substance might we classify this as? Oh gosh, what's that? It's not that, it's nowhere near a weak base. It's a strong base. Why is it a strong base? It has hydroxide ion available to it, right? Now, if you recall, what are the strong bases in general?
Group 1A.
Group 1A, the alkali metal hydroxides are all completely soluble. Consider those to be strong bases. I said some of the alkaline earth metals are also considered strong bases, but there is, for a couple of them, a solubility limit, meaning that they're not very soluble. To the extent that they do dissolve, they're strong bases. You're just limited by their solubility. As it turns out, calcium hydroxide was that main one that I was referring to. Okay? Calcium hydroxide will dissociate into two hydroxides, but it has limited solubility, as we're going to find out. Okay? So here we go. To write the dissociation, we would come up with this. Okay, which I think you guys see clearly enough. As it turns out, what is something we could measure about this solution that might give us an indication of the hydroxide ion concentration? Yeah, we can calculate the pH. So we stuck a pH meter in here. We find out that the pH of this solution, I won't even do it there. The pH of the solution ends up being 12.32. Okay, what does that tell us? It's pretty basic, isn't it? I mean, it's right up there. It's not up into the 13 or even close to the 14 range. Again, that's because of the limited solubility, as we're going to find out. But it's a pretty decent base, okay? So anyway, now all we need to do to plug into our KSP expression, which is the concentration of the calcium ion times the concentration of the hydroxide ion squared, we need to know these concentrations. How can I get the concentration of the hydroxide ion?
So you have to
Take the inverse log of the hydroxide ion concentration. So if you remember, that's using your 10 to the x key, which turns out to be, well, that's a pH. We need to find out the pOH first. So to find the pOH, remember we're going to have to take 14 and subtract from that 12.32, which turns out to be what, 1.68?
Yep.
Everyone hunky-dory with that? Okay, so now we plug that in here. Now remember, it's going to be negative 1.68. Okay, remember that piece. And it turns out that the hydroxide ion concentration, when I do that, and we'll verify each other, I get 0.021. So it's 0.021 molar hydroxide ion. So we now know this. What's the other thing we need to know? Well, a calcium ion. For those of you that do this in your head, you came up with half of that, right? But just because I know some people prefer this, I'll go ahead and do it. Let me see, what is it? 2 moles hydroxide, 1 mole of calcium. As we already knew, it comes out to about that. Okay, so now we know the concentration of the calcium ion. It's just a matter now of plugging things back into our, oh, my bad. Okay, it's just a matter of plugging things back into the expression. So the KSP is going to be the 0.0105 molar for the calcium and the 0.021 molar of the hydroxide ion. That quantity squared, Ryan.
Yeah.
Okay, and what'd you end up getting?
4.56.
Okay, so, you know, with significant figures, we'll go 4.6 times 10 to the negative 6th as our KSP. What does that tell us about the solubility of the calcium hydroxide relative to the previous question we did? It's significantly more soluble, would you agree? Okay. But again, it's not incredibly soluble. We're talking about a millionth here, right? We're 10 to the negative 6th. Okay. Okay, it's pretty straightforward. Would you guys agree? It's just applications of all the things we've been doing. I mean, this is awesome stuff. This is why I said equilibrium is awesome. You guys can do a lot of stuff with this. All right. Any questions before I go on to the next thing? Okay. I believe the next one I did ended up being, yeah, let's look at the calcium fluoride example. Now, in this case, we're going to go a little bit different direction. We've been calculating KSPs so far, you know, again, which are ways that, you know, through some experimental data, we can find out what the KSP of something is. We can also go the other way and try to find out what the molar solubility of something is based on its KSP. So in this example, we're provided with the KSP for the calcium fluoride. Turns out to be 1.5 times 10 to the negative 10th. Notice I put at the 25 degrees Celsius, just to remind everyone that all these values are at 25 degrees Celsius. What typically happens to the solubilities of substances as the temperature increases? Most will increase. There are always a handful that decrease, but most will increase. Anyway, this question is asking you to calculate both the molar solubility and the solubility in grams per 100 milliliters of water. Okay, so let's go through this process. Not that, I think a lot of you, I'm going to go ahead and do this because I think it will help you figure out what's going to happen. After you've done enough of these, you can almost kind of skip this step. But I think for now, it's going to be very beneficial for you to look at it. We do not know what the KSP is provided as 1.5 times 10 to the negative 10th. Initially, we have 0 of this, 0 of this, obviously. Okay? How is that going to change? Well, this is going to increase by x, and this is going to be increased by 2x, so that at equilibrium we get this. When we write our equilibrium expression, we get the concentration of the calcium ion times the concentration of the fluoride ion squared, which ends up being x times 2x quantity squared equals 1.5 times 10 to the negative 10th. Please be careful here. We already saw people mess this up a little bit on the quiz. What is this quantity equivalent to? 4x cubed. Very good. I'm waiting for the shock to be overcome. Everyone sees that, right? Okay, some of you see that. This is 4x squared times x gives us 4x cubed. Really soon, if you do enough of these problems that I've assigned out of the book, you're going to recognize right off the bat, you see 3 ions, you're just automatically going to call that a 4x cubed problem. Because no matter what happens, that's what you're going to get, right? No matter what the ions are, you're going to get a 4x cubed problem. Okay, with that being said, what is, I'll ask here a little bit. Let's find out what the value for x is. See if you guys can match up with what I have.
3.35 times 10
Did you get 3.35?
Yeah.
Yeah, it might be. That might be right.
That's what I got.
Is there anything after the 5?
It's 3.47.
Ah, so 3.5 or 3.
3.5. Well, I got
3.347,
Yeah.
so that's 3.3. I'll show you why here in a second. Times 10 to the what? Thank you. So you had 3.347, right?
Yeah.
We're looking here for rounding purposes.
No, yeah, I know.
Okay, okay. Anyway, so there we go. X is that. Now, what is X? Well, here's the key. X is equivalent to the calcium ion concentration. Would you agree? However, since it's a 1, this is important. Since it's a 1-to-1 stoichiometry, this is also equivalent to the calcium fluoride concentration. Does that make any sense? Okay, that's key, because what are we trying to find? We're trying to find the molar solubility of the calcium fluoride. We're determining the molar solubility of the calcium, and because of the stoichiometry, it's the same thing as the calcium fluoride. So anyway, that turns out to be 3.3 times 10 to the negative 4th molar. Now remember, 3.3 times 10 to the negative 4th molar equals 3.3 times 10 to the negative 4th moles per liter of solution. Now, is that very concentrated? Because remember I said the second part of the question is, hey, let's calculate the solubility in grams per 100 milliliters of water. Okay? We're going to make a little leap of faith here. We're talking about 3/10,000ths of a mole. That's not very much. So if I had 1 liter of water and added 3/10,000ths of a mole of this material to the water, how's the volume of the water going to change? Insignificantly. Will it increase? Yes. But it's like sprinkling a couple little crystals on it. It's not going to increase to any amount that we're going to be able to measure. Does that make any sense? Which, because of that, we're going to be able to make this leap here. Now let's go ahead, and there's the molar solubility. Let's go ahead and find the solubility in terms of grams per milliliter, or 100 milliliters of water. So we're going to take our 3.3 times 10 to the negative 4th moles per liter of the calcium fluoride. We're going to have to calculate, obviously, or convert our moles to grams. Does anyone remember? Oh, you already did it. Okay, so you add up all the atomic masses, turns out to be 78.08 grams per mole of the calcium fluoride. Awesome, so our moles cancel. But now we need to convert our liters to 100 milliliters of water. So it's going to be 1 liter up here. And what's going to be down here? 0.1. I'm just going to call it 0.1 liter, which represents 100 milliliters. You guys okay with that? I'll put in parentheses here 100 milliliters just to remind you. And off we go. Did anyone finish that yet? That's what I got.
I got 0.26.
Yep. Now, notice how I labeled that. 0.26 grams of the calcium fluoride per 100 milliliters of water. Again, that's just taking a little amount of this and kind of sprinkling some on the top a little bit. You guys agree? Okay. This is not hard. I hope you're seeing that this is not hard. As you guys are starting to recognize now, it's, okay, I've got this vast amount of knowledge. When do I do what? And that just comes from you guys practicing and practicing and practicing and practicing. All right, I'll let you guys have one chance to practice now. I think the next thing I have is example 11, which you're going to find out is incredibly similar to example 10. Why don't you guys go ahead and try that one on your own? Or you can whisper to people across the room, either way. Can't go, it's got a senior meeting.
Sure, wait, man. Then you know anything about the senior meeting?
Nope.
You always go if you need to.
Nope, I'm sure it's only one period. I don't know. I know nothing. I tried to find out, but I don't have access. Hey guys, seriously, while we're in here, let's go ahead and try to focus on this stuff. What if you're late to a senior meeting? No, what I'm saying is, let's work on this now while we're here. We'll worry about the senior meeting later.
Good morning, and pardon the interruption. The senior-only meeting has been moved to the auditorium. Again, senior-only meeting has been moved to the auditorium.
Anybody care? Nobody else care? So what do you like?
All right, everyone get that done?
Once partially, almost done.
So it's partially soluble or partially done?
Partially done.
Or both? If you get an answer for the molar solubility, shout it out.
I got
9.3.
9 point what?
9.3 times 10 to the negative 6.
Boom! There it is. See you guys tomorrow. Darn it. I wasn't anticipating a
I don't know, 'cause I think
senior meeting, so I had one more thing to do and then go over the,
Well, yeah.
yeah, those problems. Did you try those problems? How'd it go?
Some of them were pretty tricky. but
Okay,
For the
well-
most part, it wasn't bad. I think.
Right, I'm sure I put at least one that was maybe thinkable. That's what I do.
Which helps.
A couple of them should have been pretty straightforward.
Yeah, the first two
All right, well, I guess we'll look at those tomorrow if we have time.
Mr. Lane,
Yeah.
for the next answer, I got 1.8 times 10 to the negative 4.
I did not. Did you use 195.91?
90
Close enough?
times 1 liter over 0.1 liter.
Yeah, one of us is gonna have to relook at that.
I've had 9.28.
10 to the negative fourth, 10 to the negative third. The point, the one and the eight, try that again, because the one and the numbers you have are fine. The digits you have are fine.
Oops, I already know what I did.
Okay.
I times it by 0.1 instead of by.
Ah.
So it's 0.02.
0.018, yep. Again, this stuff is not that difficult. Have you guys tried 11 through 14 yet?
Yeah.
I'm gonna just do it.
Yeah, I would highly suggest that. Jeff? It's kind of fun, isn't it, knowing what's going on? and honestly, for you to make a decision as to when to wake up, this is the time. This is good.
I actually had a question though.
Okay.
With that, with electrochemistry, you know those half reactions?
Right.
Where it has the bolts?
Yeah.
And when they give you them, they're both positive for the reduction? Like any
They
equation-
might be positive, they might be
they're gonna
negative.
ask you to find the
overall.
Yes.
Yeah.
I used to always have problems with it, like which one to switch to the negative. Is it always the reduction one? That you switch to negative?
No. Well, listen, they're both reductions.
So no, one reaction is an oxidation, the other one's a reduction that they give you, right?
You want to reverse the more negative one.
So the smaller one, basically.
Listen, well, okay, if you want to go that route, yes.
So if you have a 0.78 and one's like 0.58, you reverse the 0.7.
You want to
or
reverse the
0.58.
more negative one.
Okay.
The reason for that is you need to end up with a positive E cell. So if you reverse the
Yeah, so you
more
just have a
positive,
negative.
for example, let's just play with this.
Yeah.
Let's say you had like a negative 0.25 and a negative 0.18. Which one is the more positive?
The 0.25. Oh, 0.18, sorry.
The 0.18?
Yeah.
You sure? I'm just asking.
Yes.
Wait a minute, I may have said that wrong. Did I say reverse the more positive? Is that what I was saying? You reverse the more negative.
Yeah.
You reverse the more
You don't want a
negative.
negative either.
So which one's the more negative?
The more negative one is
5, right? So we're
Yes.
going to reverse that
Some
one.
would be
So when we add it, ends up being positive.
So the positive 0.25 and the negative 0.18.
Right.
Okay.
So you make the
So you still
more
always miss that.
more negative reduction potential into an oxidation.
Okay. Yes. that makes
Now
sense.
there's a little equation they give you in the book. You look this stuff up and online, they might give you a little equation.
So you still- I
It's
always
easier
miss-
to just remember, reverse the more negative one.
Mm.
Or if in doubt, fiddle with it until you get a positive.
Yeah. So I missed that so much on the tests. Making that.
Right.
Can never figure it out.
Ah!
Oh. Wow, okay, dropping everything.
So when do I see you guys next week? Do you guys know yet? I mean, I can look it
I
up.
don't know.
Okay.
I think Tuesday and Thursday,
I think you're right.
because Monday, Wednesday, Friday are all, well, Monday and Wednesday are 1, 2, and then Monday is 7, and then Friday, Monday, Wednesday is 9, and then Tuesday, Thursday is 3,
It's the
4.
same schedule each week, I think, isn't it?
Yeah, except for Friday is a little funnier in that
Because we have the 2-hour.
2-hour delay the first day,
Right.
Really?
the first Friday, second Friday it's first period, third Friday it's second period.
Okay.
And I found out today that Mr. Blackburn is going to be out until the end of the year, basically.
Really?
Yeah,
Why is that?
no, he's just taking a bunch of sick days, and we have a sub schedule till like the 19th
Really?
of May.
I did not know that.
So that's pretty much, Econ's pretty much become a study hall.
Ms. Meyer is probably gonna be my math teacher. She got summoned to court over those, it's like the kill group or something like that. Is what my dad said it was. It said if she does get picked for trial, she'll be there for like 10
Oh,
days.
you mean like jury duty?
Oh, yeah.
Is that what, okay.
Oh, you thought she'd, no, jury duty, yeah. Yeah, she'll be gone for like 10 weeks is what they said.
Really?
Yeah, if she gets picked. She tried to get out of it saying I teach high school, and they're like, oh, they're old enough, they'll be fine.
You know, they just have, these standardized tests. Don't worry about it.
Yeah, don't worry about it, they'll pass, don't worry about it.
Although I think she does just mostly college algebra, doesn't she?
Yeah, that's
Holy
what.
crap. Hello. Are we not learning anything?
No.
We are, did you do 11 through 14?
No, not yet.
He's not gonna let you leave.
I
He's
know.
supposed to do
I
something.
wasn't planning on leaving.
By the way, I should probably not record.